Section 17.4, beets. This is not about a root vegetable. This is way more sick beets than that. All right, so we could imagine if we have two tuning forks. A tuning fork is metal bars that are carefully constructed to have a pure tone, that they'll naturally sound one frequency. So here we have one that's 440 hertz, and we have an identical one, but there's been added a small piece of putty, so it's not able to vibrate quite the same way it normally would. And that's enough, it turns out, to reduce the frequency down to 438 hertz. Well, if we have two overlapping waves with very slightly different frequencies, we get the phenomena of beats. I want to try and show it to you. I don't know that it will work properly over Zoom, but we're going to try it because it's worthwhile. It's that cool. So with 440 and 438 hertz, I apologize, there's a little bit of a buzzing sound, but you can still hear the beat through that. So that clicking sound is not the beat. This is just the normal trying to sound 440 hertz. So listen to that pure, that's what we want to key into. Now we're going to add in 438 hertz and see the effect on the pure frequency. So notice it gets louder and quieter. This is what happens with beats. A beat frequency is where there's this loudness that rises and falls periodically. The ear is hearing a combination of two different waves. And so the combination has this overarching envelope that the number of times per second that that you have the loudness rising and falling is known as the beat frequency. So we could write that here. The beat frequency is the difference, it turns out, between the two sound frequencies. And here's this really nice depiction, right, where there are 10 hertz and 12 hertz waves. And so at times, notice the waves are totally out of phase, like at the beginning, so it's really quiet. But then there are other moments, like at 2.5 versus 3.5 for the lower wave, where they're exactly in phase. And so as time passes, there's both destructive and constructive interference because they have these two frequencies that are very similar, but not quite the same, which is really cool. So we could think, okay, if one of them, like F2, is 440 hertz, and the other one is 438 hertz, what's the beat frequency? It's 2 hertz, right? That means that we're hearing two loud and soft, right, times per second. And you can actually time it, right, with a stopwatch and be like, oh, like gain louder and softer 2 times per second. What if instead of 438, we lower it down to 437? Then it'd be 440 minus 437. We'd expect 440 minus 437. That would be now 3 beats per second. That should be faster. So we can actually test that. If we see here 3 beats per second, what if instead of going down, if we go the other way, 440 minus 439, well, then that should only be 1 beat per second. It's going to actually slow down how fast it's getting louder and softer, coming in and out. We're going to try it briefly. I encourage you to also try this in your own time because it is super cool. So I'll stick with the 440 and I'll start with 438, the 2 beats per second, and then we'll switch to 437 and then go up to 439. Right, so it's getting louder and softer in there. Now I'll go down to 437. And it starts going faster there. If I go to 439, then you can really hear that effect of it coming in and out, louder and softer. actually what musicians do when tuning. They listen to those beats and they try to slow the beats down because that means the frequencies are matching more and more closely until there's no beats. There's just the exact same sound. So, this hopefully gives you some cool ideas to try out. Please try not to annoy your neighbors or housemates with it. Um, but you can just say, you just got to drop those sick beats.